So far we've been talking about monoprotic acids, and now we're going to address polyprotic acids. These have two or more ionizable protons, two or more hydrogens at the beginning of the formula. And those ionize in successive steps. So this is sulfurous acid. It's got two hydrogens here. It can lose one hydrogen to form hydrogen sulfide ion. And there's an equilibrium for this and an equilibrium constant. And then the HSO3 also has a hydrogen, an ionizable proton, that it can lose to form sulfide ion. And this has a separate equilibrium and a separate equilibrium constant. The second equilibrium constant is always much smaller than the first one. And we can explain this by noticing that this hydrogen is leaving a neutral molecule, whereas this hydrogen is leaving an anion. So you have a positive charge trying to get away from a negative charge, and it's just going to be harder for it to leave. Any questions? So these are common polyprotic acids. We've got sulfuric acid, and here they're giving us Ka 1, 2, and 3. Some of these are triprotic. For sulfuric acid, the first proton is a strong acid. So sulfuric acid in water loses one hydrogen ion completely, and then there's an equilibrium for the second one. The rest of these all have 1 and 2. So oxalic acid, sulfurous acid, phosphoric acid, those are ones that we're fairly familiar with. Citric acid, ascorbic acid, and carbonic acid. So you probably don't know the formulas for citric acid and ascorbic acid, but that's okay. But they are, this one's triprotic, and this one's diprotic. And then we've got carbonic acid also. So to find the pH of a polyprotic acid solution, we have to think about, well, is the first proton more important, the second proton? The first Ka is always much larger than the second or third. And so the amount of hydronium ion formed by that first step is larger, and often is the only thing we need to look at, because the formation of hydronium ion in this first step inhibits the formation of hydronium ion in the second step. So if you go back to this guy. So here, this one is creating hydrogen ion, and so this one now isn't starting with 0. It's starting with the hydrogen ion concentration that was present here. If we've got extra hydrogen ion, that's going to cause this equilibrium to shift towards the left, and so we'll get even less hydrogen ion from that one. So for most polyprotic acids, we can just look at the first step. An important exception is if you have a dilute solution of sulfuric acid, then you do have to consider both of them. So let's find the pH of a 0.050 molar H2CO3 solution, and we're given both of the Kas for this diprotic acid. So we're going to do ice table. So first we're going to write the equation for losing the first proton. So we've got the acid, and that's going to lose one proton, one hydrogen, and that will leave us with HCO3 minus. If you don't remember the charge on carbonate ion, it's okay because you can figure it out from the hydrogens. It's got 2 hydrogens to balance this charge, so that's a -2. If we lose one of these, then the HCO3 is a -1. So then we'll make an ice table, and we'll write down the initial concentrations. So here we're given the concentration of the carbonic acid, 0.050. What's the initial concentration of hydrogen ion? 0. And HCO3, also 0. Okay, so then we do the change in terms of x. This side has zeros, so that has to be the plus x side, because you can't go down from 0. And this will be minus x. We add those two together, and we get these expressions for the equilibrium concentrations of our reactants and products. Now we'll write the equilibrium constant expression. So this is Ka1, because it's the first one. So we've got H plus and HCO3 minus. And down here we have H2CO3. And we've done things just like this recently. We're given Ka1, so we can write that in for Ka1. And then these are equilibrium concentrations, and we're going to put their expressions in from the equilibrium row on the periodic, on the ice table, not the periodic table. So H plus is x, HCO3 minus is x, so I just wrote x squared. And then we solve for x. As I've mentioned before, I prefer to just use the number solver, but you can do x is small. You just have to remember to check to see that the percent is 5 or less. So x is 0.0001464. Anybody else get that number? Good. So this is a polyprotic acid solution. We can probably just consider this first ionization. This would be giving us our hydrogen ion concentration. But let's include the second one and just see what happens. So this loses one proton to make hydrogen carbonate ion. The hydrogen carbonate ion can also lose a proton. So we can have HCO3 minus losing a proton, and then we get carbonate ion. And again, we're making an ice table. The initial values here, though, are going to come from the equilibrium values over here. We were not given a concentration of HCO3 minus. That was formed by the first equilibrium. So here, X is equal to the H plus concentration. It's also equal to the HCO3 minus concentration. And we found what X is, so we can write that into this new table. So those are the initial concentrations of hydrogen ion and carbonate ion. This is different than what we've done before. Is everybody okay with why? How that happens? Yeah.
I'm confused on why we started with the HCO3 minus instead of the H2CO3.
So we did the H2CO3 first. So it's going to lose one proton and make HCO3. Now we're going to recognize that this also has a hydrogen. It can also act as an acid. So we're going to take this guy over here and look at it losing that second hydrogen.
So it's kind of like a second step.
Second step, exactly. Yep, thanks for asking that. Any other questions? So our initial concentrations for these two come from the equilibrium concentrations of the first ionization. They're not going to be zero. What did I do wrong? I just saw it. I did something wrong. HCO3 is X, and I wrote this under CO3 2 minus. That's just wrong. Oh, sorry about that. You can fix it though. There it goes. Okay, that's better. These are the two products in our first equilibrium. So we put their equilibrium values in here. Let's just move the ice over. It's a little squishy. What's the initial concentration of CO3 2 minus? 0. We don't know anything about that, so that one's going to be 0. Okay. So we have a 0 initial concentration, so we know that that one has to go up. That one has to be plus X. And then this guy has to be plus X. I guess I kind of gave up really should have that line there. So this line is just separating the reactants from the products. So if products are plus X, they all have to be plus X. And that means that all the reactants would be minus X. So then we get 0.0001464 minus X and 0.0001464 plus X and X. So that's one line. Any questions about that? So whatever equilibrium concentrations we get from the first ionization, those will be used as the initial concentrations for the second one. The second ionization. Well, so this guy loses one hydrogen to make this. We come over here and we say, okay, what does this do when it acts as an acid? It loses a hydrogen, and then this is what we have left. So then we see, oh, this one and this one were both at the end of this one. And so we have values here. If for some reason we had H2CO3 in here as well, we could come over here and say, oh, well, 0.05 minus X, that would be the concentration of H2CO3. But we don't need it for this one. Does that make sense? So you got an acid, you recognize it because it starts with H. You take off one hydrogen, and the other product is whatever's left, right? It could be some crazy formula. Just take off a hydrogen and reduce the charge by 1. That's what you've got. Then you're going to take this guy that has a hydrogen, and that's now an acid. And so you're going to look at that, losing a hydrogen ion, and it'll give whatever's left when you take the hydrogen ion off. We see that these two, we have concentrations at equilibrium that are not 0. And so we write those in. This one, we've gotten no information about, and so we write 0, because this didn't make any CO3, 2 minus, and we didn't have any to start with, so that one's 0. Then we do the X changes as usual, and we add those together. So there's a little bit of a difference in the middle, but overall it's the same process. And then we're going to write the equilibrium constant expression for this second equilibrium. So this is Ka2. Writing with a highlighter just, it doesn't work very well. Ka2, and we're going to write this just from this equation we've got up here. H plus CO3, 2 minus, divided by HCO3 minus. So we write the equilibrium constant, it's the products over the reactants. And that's the second equilibrium constant. So then we can plug the values into that. Whoops. Ka2 is 5.6 times 10 to the minus 11. And now H plus is this kind of messy thing here, 0.0001464 plus X. And CO3 is just plain X. And that's going to be divided by the HCO3, which is that guy. You can plug this into the solver. I've done this a lot, and so I recognize that this is a situation where using the X is small approximation makes the math much, much simpler. If this X is 0 and this X is 0, then these two numbers cancel out. And X just equals the equilibrium constant. But if you don't think of that, and you don't like X is small, you can plug it in and it'll come out really close. So X is small, that means this is essentially 0, and this is essentially 0. And then these numbers cancel out. So X is equal to that second equilibrium constant. I did the X is small approximation. I need to check and make sure that it's valid. Yeah, it is. I'm going to check anyway. 5.6 times 10 to the minus 11. And I'm going to divide by this number that I was adding to or subtracting from, 0.0001464, multiplied by 100. That's 0.00004%. Minuscule, right? So if I want the hydrogen ion concentration here, I would take this and add X. But X is so small that it doesn't matter. Whoops, did not mean to do that. So, because what we're doing there is we've got 0.0001464 and 0.012345678910. 56. When we add these two numbers, does that make any difference at all? No, it doesn't, because this 4 is where the uncertain digit is. You have a question?
For the X is small, to do the checking, can you go over the formula for that?
Yes. Let me make some space up here. This slide is getting very crowded. Goodbye, title. I don't need you anymore. So to check the X is small, I'm going to take the value of X, 5.6 times 10 to the minus 11, and I'm going to divide it by the number I was adding it to or subtracting it from. Here, those are the same number. If they're different numbers, use the smaller one, because that's going to give you a bigger percent. So I'm going to divide by 0.0001464, multiply by 100, and I got 4 times 10 to the minus 5th percent, which is far, far less than 5%. So this is the check on X is small. You know, if you were doing an exam and you didn't check it because you're like, I'm pretty sure it's small, I wouldn't notice, it'd be fine. Okay. If you were showing your work on a problem, as long as your guess was correct, I wouldn't object to you not writing that out. Okay. Any questions about this? The X is small validation. So over here, this is just kind of proving that X is small. If we try to add X to this number, it doesn't change, does it? I accidentally used a different purple. Oh well. So there's our last significant figure, right? Did that 5, 6 way down at the end matter at all? It didn't matter at all. So we end up saying that, well, let's choose yet another color, that the hydrogen ion concentration is equal to 0.0001464. That's the answer we got from the first ionization. So this is what the previous slide was saying. We can almost always ignore the second one. The second one has a much smaller equilibrium constant, and it's going to be inhibited because the hydrogen ions produced by the first one are going to make this shift towards the left. And so it's going to make even less than it would have otherwise. So this is just demonstrating you can ignore Ka2 if you're calculating the hydrogen ion concentration. So then to find the pH, here's our hydrogen ion concentration. We're going to take the negative log of that. 1, 2, 3, 4, 6, 1, 4, 6, 4. pH 3.8345. 2 sig figs, so 2 decimal places on the pH. Personally, I really like significant figures because there's a small set of rules and you follow them, and that's all you have to do. I know a lot of students don't feel that way, and so if you're not good with sig figs, you don't like them, just always write down a couple more digits than you think you should. Because if you got this as your answer on a multiple choice exam, and this was the closest answer, you wouldn't have a problem with that, would you? No, not at all. You had a question over there.
Yeah. So for defining pH, you did the negative log of that number, right?
Yes.
I thought that was a pOH.
That's a good question. So, student is asking, well, wouldn't this be the pOH? Well, we were doing bases on Monday. And when we were doing bases, we had hydroxide ion over here. And so then our X ended up being hydroxide ion. But here, it's hydrogen ion. So when we take the negative log of the hydrogen ion concentration, we get pH. When we've got the bases, then we've got those kind of 2 extra steps we have to do to get from pH to pOH. Good question. Anybody else? So, yes.
So in the case of this, like say it was like a test on an exam or a question on an exam,
Mm-hmm.
would you want us to do the whole second
good question.
concentration was correct.
If this was an exam question, would I want you to do this whole second part? No.
Okay.
No, I wouldn't. Weak acid, just use the first, diprotic acid, polyprotic acid, just do the first one, and that one's gonna be the pH, okay? You don't have to do the second part. What we'll find, though, is that some of the questions are kind of mean, and so instead of asking you for the pH, they'll ask, what's the carbonate ion concentration? And then you have to do the second part. You guys ask really good questions. I appreciate it. Dilute H2SO4 solutions. This is the one exception that you need to remember. For a dilute H2SO4 solution, you have to consider the second ionization also. You can't just look at the first one. And this one's going to force us to do that anyway because they're asking us about the SO4 minus. Okay, so we've got sulfuric acid solution. We're going to write the chemical equation for sulfuric acid acting as an acid. So H2SO4 loses a hydrogen to become HSO4. Oh, but wait. H2SO4 is a strong acid. So we don't want this equilibrium arrow here. That's going to be a single arrow. Sulfuric acid loses all of the first proton. All of them do that. It's a strong acid in the first proton only. So if we have 0.0075 molar H2SO4, how much HSO4 are we going to end up with? We don't need an ice table. Yeah, we're going to end up with the same number. Because this is H2SO4, and there's 1 mole of HSO4 for every 1 mole of H2SO4, and so it ends up being the same. And that's going to be equal to the hydrogen ion concentration as well. Put it like that. So, this is a little different. Sulfuric acid, the first proton comes off. So the hydrogen ion concentration and the hydrogen sulfate ion concentration are both going to equal the original concentration of the acid. You don't necessarily have to show any work for that. So that's just me trying to show you what's going on in my head. Just a little tiny part of what's going on in my head because there's an awful lot of craziness up there. So now we're going to look at this guy. I don't want to do that. Come on. We're going to look at this guy. This has a hydrogen that it can lose. So HSO4 minus will be in equilibrium with H plus and SO4 2 minus. When we have more than one hydrogen here, they come off in separate reactions. So here we're losing one of them, and then we're taking this guy, and that's losing its hydrogen separately. So this is a weak acid, so we do need an ice table. We didn't need an ice table here because that's a strong acid. A clue, if you forgot, is they gave us Ka2, they did not give us Ka1. They didn't give us Ka1 because it's a strong acid and it has no numerical value. So it's not just that they forgot to give it to us. We didn't need it. It was strong. Okay, so ice table. This is not the first thing happening in the solution, and so we're not just starting with zeros, right? We're going to look at what happened after the first one. Well, the hydrogen ion became 0.0075. And the hydrogen sulfate ion is also 0.0075. When the sulfuric acid ionized, it separated completely into hydrogen ions and hydrogen sulfate ions. So this initial 0.0075 moles per liter produced 0.0075 moles per liter of HSO4 and of H+. And so those are the initial values down here. You guys follow that, kind of? What's the initial concentration of sulfate? 0. So now we put the X's in, we're back in more familiar territory. So this one has a 0, it's got to be plus X. So this one has to be plus X, and that one's minus X. Write the equilibrium constant expression. So Ka2 H plus times SO4 2 minus divided by HSO4 minus they told us Ka2 was 1.2 times 10 to the minus 2. And so then we've got H plus 0.0075 plus X, and the SO4 minus is X, and down here 0.0075 minus X. And we could look at this one compared to the one we ended up with on the previous slide and say, oh, well, if X is small, this would really become simple, wouldn't it? X would just be this. But this is a fairly large equilibrium constant. So if X is 1.2 times 10 to the minus 2, we would have to divide it by 0.0075, multiply by 100, and we get 160%. X is not small. So we can't ignore it on a dilute sulfuric acid solution. So we have to go through and use the solver or whatever alternate method you have for figuring these things out. .0075 plus X times X 0.0075 minus X. X equals 0.003854. Anybody else get that number? So X, in other examples, X has always been like directly related to all the answers, right? And so we might be tempted to say, oh, well, X is the hydrogen ion concentration. No, it isn't. The hydrogen ion concentration is 0.0075 plus X. What we found here, that's the sulfate ion concentration. So that's the SO4 2 minus, which is one of the things they asked us about. So that is part of an answer. Or a new one. Okay. So let's add those together. And we're going to get 0.01135. So the pH is going to be the negative log of that. One 1.94486, 1.945. So the sig figs got a little tricky there. This had 2 sig figs, that has 2 sig figs, but we're adding them. So we have to look at the decimal place. This one had 4 decimal places, this has 4 decimal places. That has 4 decimal places. So that gives us 3 sig figs now, and that's why I put 3 decimal places on my pH. I won't try to trick you with stuff like that, but it happens, and I'm not just making stuff up there. It was actually a real thing. So that's the pH, and this is the sulfate ion concentration, which actually we should round that appropriately. 3.9. They gave 3.86. I don't know why they did that. I disagree with their sig figs. Any questions? So you have to do it this way for sulfuric acid, dilute sulfuric acid. So we see that this concentration is 0.0075. That's pretty small. Something like 0.1 would be considered fairly large. And the reason we still have to consider this is because that second ionization constant is actually still pretty big, 10 to the minus 7. The last one we looked at was 10 to the minus 2. The last one was like 10 to the minus 10 or 11 or something, right? So much, much smaller. Any questions? So finding the concentration of the anions for a weak diprotic acid solution. So for whatever reason, we may want to know the concentrations of the anions. Why would we want to know? Because there's an exam question that's asking us what they are. Otherwise, you probably don't care, and that's fine. So here's a generic diprotic acid, H2X, right? And so that loses a hydrogen to form HX minus. That has a first ionization constant. Then the HX minus loses a hydrogen to form X2 minus, second ionization constant. So for the first ion, you're going to calculate H3O plus like you would for a weak monoprotic acid. The concentration of HX minus is the same. You're going to do an ice table, and the answer will be in the ice table. Okay? Then the second one, this is what we did for the sulfuric acid and what we did unnecessarily for the other one, where we take the second thing. So we're going to take this guy, right? This acts as an acid. We're going to make an ice table for this, but now we have to use these concentrations from the first equilibrium as the initial for the second step. find the CO3 minus concentration of the 0.05 molar H2CO3 solution in the for practice 17.7. So this is the first one that we did. Let's do this instead. We did all that stuff, right? Let's just go over it real quick. We had a 0.05 molar carbonic acid solution. We had 2 Kas. We took the carbonic acid, took off 1 proton, we get HCO3. We made an ice table. We wrote the equilibrium constant expression. We plugged these values in for X. We solved for X. Then what we did not have to do here is go on further. But that other question that's referring back to this one is asking, what's the CO3 minus concentration? Well, this doesn't tell us that. So then what we do is we use the results of the first ice table as the initial values for the second ice table. So this was X and this is X. X was that number. So here we've got that original value of X, the original value of X, and 0. Because these were produced by the first ionization. Everybody okay with that? So these come from the first ionization. Now we just go ahead and do the ice table here. So this minus X, this minus X. And we write the equilibrium constant expression, and we plug all those things in. And then we looked at X is small, and we found that, yeah, X absolutely was very small. Well, X here is that carbonate ion concentration that we're trying to find. So this is the answer for the carbonate ion concentration. That's X. Any questions about that? If we were just looking at that second problem, find the carbonate ion concentration, we would have to do all of this from the beginning. And so they're asking us about this question that we already did so that we don't have to do the whole thing over again. Any questions? So, let's see, what's up? I don't know, I've used up all the colors. So this is the carbonate ion concentration. So let's go back, and there it is. 5.6 times 10 to the minus 11. Any questions about that one? So polyprotic acid, you can ignore all but the first ionization unless it's dilute sulfuric acid. You can just do the first ice table. But then there's questions like this, which aren't asking you about the pH, they're asking you about the concentration of ions. And here you do have to do the second ice table. So we need to know how to do the second ice table. Bless you. So let's look at the dissociation of a polyprotic acid. So here's a diprotic acid. It's got 2 H's up here, right? It loses 1 hydrogen to form hydronium ions, and then we've got this anion. So in this example, it was 0.1 molar acid, and they're using the equilibrium constants to do the calculations for us. So you would make an ice table and you would find out that the hydronium ion concentration resulting from this is 2.8 times 10 to the minus third molar. The second ionization, now we're starting with some hydronium ion here. We've got 2.8 times 10 to the minus third molar hydronium. We also have 2.8 times 10 to the minus third molar of this ion. And so that's going to affect that equilibrium. We do an ice table. And here we find that the hydronium ion concentration is 1.6 times 10 to the minus 12. So the second ionization only gave off a teeny, teeny, tiny bit of hydrogen ion. That's far less than what's in pure water. In pure water is 10 to the minus 7. This is 10 to the minus 12. So the total hydrogen or hydronium ion concentration for this will be the sum of those two things. This one is so small that it doesn't matter. So we can skip that unless they're asking us about the ion concentration. Even if they're asking us about the ion concentration, there's still kind of a shortcut, because since the amount of hydronium from the second step is insignificant, the concentration of that last anion is going to be equal to Ka2. That's what we found here. This was the anion. That's the same number as Ka2. Any questions?